My name is Karthik Gandhi. I work at Uber as a software engineer. I am part of the storage team. I joined about 2 years ago, and since then it was a small team, worked on infra primarily, and then infra went into different directions, security, fraud, storage, compute, and I ended up in the storage side. So this talk is primarily about how we consolidate our compute resources and manage our web applications as well as a stateful service such as Cassandra on top of Mesos. So if you don't know Uber's mission, it's transportation as reliable as running water everywhere for everyone. So this is something we came up with 2 years ago as well, and that's where we started the whole consolidation. Reliable, yeah, you click a button, food shows up, you click a button, car shows up every time. It's magic. We want to keep it that way. So at that time, we had a monolithic stack, a UI, a middle API layer, and a Postgres database. Didn't really scale well at the rate at which we were growing. So we decided to split that up so that we can be 4 nines available and support our users effectively. Everyone, so we need to keep our costs down. So if you don't know, Uber manages its own data centers. We had a few data centers, and we don't have anything in the cloud. So it's very important for us to keep the infrastructure cost down. So consolidation is really important in a way. So before I jump into the presentation, a little history about cluster management at Uber. Earlier, there was no management system. Basically, we had a bunch of systems rented out from a co-location, and then we statically partitioned them out to the API layer, the UI layer, and the storage layer. And usually it's over-provisioned, they don't scale, they fail often. And to say a simple example, you can identify a service or identify who's running on which server by identifying by looking at the name of the server. So it was that way. But then, the paper came out from Google, from Borg, and I used to work at the Autopilot team of Microsoft as well, which are, Borg and Autopilot are cluster management systems. We started looking into it. So the paper said, if you use a cluster management system, it can lead up to 30% reduction in resource utilization in terms of infrastructure. So that kind of got us curious. And since I've actually seen that work, we decided to give a cluster manager a try. At that time, we had 2 options. One was the Kubernetes, and the other one was Mesos. The choice was really simple because Kubernetes wasn't mature enough, and it only supported 500 machines, which didn't really work for us. So we decided to go with Mesos at that point. And also, we just hired the first author of the Borg paper at that time. So, yeah. Before I jump into the details, I want to give you a little perspective on why we do this. What problems prompted us to look into Mesos or Cassandra and all the infrastructure management. It's primarily, I think, into a few buckets. One is, if you want to just run one cluster, like a Cassandra cluster, you don't need anything. You can just pick up 5 machines or 10 machines and just copy the Cassandra binary, run /Cassandra, and that's it. You're done. You don't really need anything. If you want 5 clusters, you can have a Puppet or a Chef go and deploy those 5 clusters and write a few scripts, and you are done. But these kind of systems are necessary. You have to graduate from the scripts to a system when you scale out. And that's where we were precisely 2 years ago. So that's why we had to look into a system that really scales well. And that's the perspective that we had at that time. How do we scale out to hundreds of clusters while supporting 2,000 plus services and 2,000 plus services and reliably? So that is where we started. And if you're not going to be running at that scale, everything I'm going to say is just overkill. But that's the perspective, and it takes that perspective to appreciate what has been done to support Cassandra reliably. So how many of you are not familiar with Mesos? Wow, everybody's familiar. Okay, great. Okay. All right. So I'll give you a little introduction. So Apache Mesos is called a distributed operating system of sort. It's also called a data center operating system. What it does is it abstracts all the hardware resources below that and provides a unified API out. So imagine, this laptop, we have a Mac operating system which abstracts all the hardware resources. Mesos, on the other hand, just goes one layer up and masks about 10 or how many ever machines that you have in a data center. So a Mesos deployment has two core things. One is containerizer, the other one is the allocator. You can think of a Mesos container as a process that's running on a single laptop. The unit of scheduling for a Mesos master is a container. So that's the unit of scheduling, and the allocator is the one that kind of manages the resources and schedules these containers across the resources that it manages. So that's kind of what it is, a distributed operating system. So framework, so if you can see the framework, what a framework is I can give you the analogy of a music player or a web browser on this laptop. So those are called applications. The operating system in itself is not very useful without the application. So a framework in essence is an application that's running on top of distributed operating systems such as Mesos. It's a simplified explanation, but kind of gets the point, I guess. So in a typical Mesos deployment, what we have is a Mesos master. And as part, when I say a Mesos master, it's just a bunch of machines in which a Java service called Mesos is running. And you have a bunch of physical machines. These are hardware, like a server, for example. What you do here is you run the Mesos agents. These agents registered with the Mesos master, and they provide whatever resources they have in that server to the Mesos master. In other words, they advertise all the resources they have to the Mesos master. A framework, on the other hand, is an application that needs to do something useful. So what it does is the framework registers with the Mesos master and says, I need so-and-so CPU, so much memory for running this task. Do you have that? And then the Mesos master says, yeah, I got so many offers from these agents, and these are all the offers I can pass on to you. So framework takes all those offers, looks at it, and says, OK, this looks like I can use it. So can I reserve this, and then can you launch this task for me on this agent? And the Mesos master says, yeah, OK. And then what it does is it goes ahead and launches the task here. As I mentioned earlier, a task is a container. Within the container is your binary, whatever you want. It can be a shell script, it can be a Java program, it can be anything. Doesn't matter. You can wrap anything in a container and just push it out, and that will run in one of the agents. So that's a simplified architecture of what Mesos is. Any question? Kind of important terminologies to remember is a framework, what it is, Mesos master, and the agent, and the executor. An executor is nothing but what you provide to the Mesos master to run on those agents. That's an executor. So some of the popular Mesos frameworks were Aurora. This was developed by Twitter. When it was developed, it was developed to be the only framework or the application to run on Mesos. What this does is it helps you manage all the web applications. You can have abc.com, you can have internal sites, anything that's stateless. In other words, if it fails, you can launch it somewhere else. So anything that's stateless can be managed using Apache Aurora. Twitter developed it, and it's being used. Uber also uses Aurora for managing all the web applications. In other words, if you go to uber.com, it's probably being served from one of the containers that's being managed by Aurora on a Mesos deployment. So Marathon is a commercial version of it developed by a company called Mesosphere, which kind of does the same thing a little bit more, but I'm not too familiar with this one. Kronos is a cron job. Again, to give you a simple example, you can write a cron job in a laptop or in a Linux system. It will keep running. The equivalent of it in a distributed system like Mesos is Kronos. You can say schedule this job periodically, and then it will just find out which agent has the resources for that task, launches it. Once it's done, just wait for the next turn, launches it somewhere else. So that's kind of a cron job equivalent. So as you can see, it was Mesos was predominantly used for managing stateless applications, web applications or cron jobs, for example, until Mesos introduced this feature called persistent volumes. So this came out with Mesos 0.23 and kind of was mature at 0.27, 0.27, version 27. That's when we started using it. What it does is, in addition to providing resources, it will also provide a sticky bit for the tasks that need to store state. So here, I took Cassandra as an example, but you can run MongoDB, you can run MySQL, you can run any task that needs state to be preserved. Here, when I say a state, it can be database or data of any sort. So it provides a sticky bit that says, this task needs this data, and this data resides with this Mesos agent. So whenever you schedule it, please schedule this with this agent. So that's the sticky bit. So that's the feature that was introduced with Mesos 0.23, and it's called support for persistent volumes. So as you can see, if a task crashes, Mesos will try to reschedule this task on the same node where it crashed. The whole thing goes out, yeah, it's gone. But if the machine is still alive, it will be scheduled on the same machine. Let me give you an example of how this works. This is a typical Cassandra in a bare metal deployment. You have a Cassandra process, and then you have a local disk where Cassandra stores commit logs, data, and cache. When I do the same here in a Mesos world, what it does is Mesos wraps it around a container and then mounts this local disk to this container. So that's the difference. Once it is mounted, let's say this process crashes, Mesos knows that this process was attached to this persistent volume, so it will relaunch the task again, and the same volume will get mounted again, and off you go. You're good. Is it clear? Any questions? So yeah, persistent volumes were the beginning of Mesos starting to support stateful applications. Yeah, it's not. This is not supposed to be a Cassandra course or a tutorial. I will just briefly cover what Cassandra is. There's plenty of material available online. But my point is, if you can run Cassandra, you can run any database. We have been running it for a little over a year now. Pretty much most of our core applications, like dispatch, for example, runs on Cassandra. So which is again runs on Mesos. So I think it's pretty reliable at this point. So when we talk about a Cassandra cluster, the core or the lowest unit that we talk about is a node. A node can be a VM container or a bare metal or a physical machine. So when it is in a physical machine, we call it a bare metal cluster. In the Mesos world, a node is nothing but a container launching one of the agents that were registered with the Mesos master. So a bunch of nodes within a same data center forms a replication unit. So if you write here, and if you want your data to be replicated thrice, it will be replicated within this ring in data center. So we call this a ring. Cassandra supports multi-data center right off the bat, so you don't have to do anything there. So the whole thing is called a cluster. So node, ring, cluster, that's enough to know. So why we decided to go with Cassandra, we wanted to be all active. We manage our own data centers, so any failure in one data center should not be affected on should not bring the whole service down. So it was important. And at that, our scale was kind of okay at that time, so Cassandra did really fit into our use case really well. So that's one of the reasons why we went with Cassandra. So now we talked about Mesos, we talked about Cassandra, we talked about how it works. So this is the whole architecture that we came up with finally. As you can see, we have a Mesos master, which is under standby master. You can have as many standbys as you want. If a Mesos master fails, the standby will just take over. This setup works very well. And the Mesos master uses a zookeeper quorum to store all the state about all the Mesos agents that it is registered with, all the tasks it has launched. So it will try to maintain all the state information in a zookeeper quorum. Aurora here is the framework, the Apache Aurora that I talked about earlier, registered with Mesos master and provides an interface for our deployment system to launch all the web applications. In other words, stateless applications are all being managed by Aurora today at Uber. And here comes our new frameworks, which is the Cassandra service framework. So with this, we can say, hey, go launch a Cassandra cluster of size 5, and it registers with the Mesos master and says, okay, I need to launch 5 tasks, give me all the offers that you got. It evaluates each offer and says, okay, this works, launch the first node, this works, launch the second node, and so on and so. So that's how the framework works. The only difference between these two is this is going to have a state, and this is not going to have any state. So as you can see, there's a common pool of resources below, and pretty much the stateful, stateless services can share these resources effectively, thereby increasing, the utilization of all the physical machines that we have within our data center. Here in this example, I'm showing 2 Cassandra clusters, cluster 1 and clusters 2. And the good thing is even they can coexist within the same machine. As long as they don't belong to the same cluster, it can coexist in the same machine. So, any question? Okay, that'd be all. So when we talk about a framework, the framework comes with two components. One is called the scheduler, the other one is the executor. So executor is the one that's responsible for launching the Cassandra task. I think I mentioned earlier. So executor takes a script or anything you give it and then launches it as a task. So here, to the executor, we are going to give a Cassandra binary. And that's all it's going to take, and then just launch the Cassandra task. A scheduler, on the other hand, is the one that registers with the Mesos master and manages all these tasks. So a task here is, again, a Cassandra node, and I'll talk about more tasks that the scheduler can manage. But the scheduler is just a task manager. It's the one that gets the state from the executor saying, this task is fine, this task is fine. If it fails, says, OK, relaunch again. So all those decisions are made at the scheduler level. Oh, okay. Yeah, I'm going to get there now. Next slide. Okay, so here are all the tasks that you can have. So it all starts with, when it comes to deploying or managing a database system, the one thing you worry about is deployment. So that is covered already. To the scheduler, you can say, launch 5 nodes, and it will find out all the resources that is necessary, and then launches the 5 nodes. The next part is operations, maintenance, monitoring. So those are all the important features that you look for in a management plane when it comes to a database. So we covered the deployment part. So what about management? The scheduler covers the management part as well, management and operations part as well. In a given Cassandra cluster, Cassandra is considered this developer's database. It's not that you can just deploy and then let it run and forever. It never works that way. We never found it that way. It's kind of more tricky to run a Cassandra cluster. So we are really thankful that we have this framework. And it's not the experience of just Uber. If you look at other companies like Facebook or, Instagram, I should be very specific, Instagram, Netflix, or Apple, they started using Cassandra at different generations, like 2011, 2009. At that time, they did not have a system like Mesos, so they decided to build everything on their own. But the idea is the same. You need a management system, and we were lucky we had Mesos, so developing something like a framework was much easier than developing 10 other systems, each doing one task. But you need a management system for if you want to scale out Cassandra clusters. So the framework comes with the features. In other words, these are all the tasks it can launch. So the basic task it launches is a Cassandra node. If you just want to increase the cluster size, you can just change the number of tasks from n to n plus whatever. And then just click, and then it'll update, it'll launch the new tasks. If you want to replace a dead node, you can just say, you can again hit an endpoint and say, okay, replace node number 2. It will just kill the existing task and then launch it somewhere else. Backup and restore, again, you can just, this works like a web app. A framework, the scheduler is nothing but a web app. It provides a bunch of API endpoints, and each endpoint is going to interact with the Mesos master and the agents and the Cassandra tasks, and it'll do whatever you want it to do. So, yeah, follow me so far.
How would you discover IP address, DNS, like service discovery, how to connect to that newly created cluster?
Good point. That's why the seed provider is here. So in a Cassandra cluster, when you launch the nodes, what it looks for, the first thing that a new node does, it looks for a seed provider. In other words, it's the node that the new node needs to talk to discover the entire topology and advertise itself. So that is a crucial point for a new node that's coming into a Cassandra cluster. What we do is we provide a custom seed provider. In other words, we don't hard code anything. All we do is we provide a REST endpoint as a seed provider. The REST endpoint is something that we have in the scheduler. So when the new node comes up, it hits this REST endpoint. And then the scheduler will say, I know about all the tasks that you're trying to know. And here are all the IP addresses. So then it knows, OK, these are all the nodes I need to connect to. And then it just goes and joins and does its thing. So it's a little hack. You definitely need that. It's a good question. If you compare it to a bare metal deployment, what people do is they statically configure. OK, when you join, this is the IP address you need to talk to. That's a static configuration. But here, you'll just configure a URL.
So what is the database size and how long it takes to replace a dead node?
That's, again, a good question. So it varies. So let's say the task can own up to 1 terabyte, 2 terabyte, how many ever terabytes. So we try to cap it at 1 terabyte because that's where we found that the replacement time is manageable. Yeah, so if it goes beyond 1 terabyte, it takes at least 2 days to replace. Because it's a lot of data streaming to the new node as well as data distribution among the other nodes. Every bit of data needs to get the synchronization part with other nodes before it moves to the new node. So kind of a time-consuming process. So we try to limit the amount of data per node to 1 terabyte. We set up alerts, and if we reach about 40% utilization, we increase the number of nodes for any cluster that we manage.
So when you say 1 terabyte, how much time does it usually take for you? Like, I hope your system is very busy, right?
Uh-huh.
So how much time it takes to drop a node and then add a new node?
So that's where the framework is really useful. All we need to do is to just change the number of nodes from 5 to 6. That's all we need from our side. If you want to increase the cluster size. If you want to replace it, again, we just hit the endpoint. That's it. We don't do anything else. The framework, on the other hand, will take care of finding the new node and then killing the existing node and just transferring the ownership over to the new node.
What we are actually trying to understand how much time it takes for the new node to come alive and take.
Yeah, right. If you have 1 terabyte of data, it at least takes a day for it to come alive. Yeah.
Do you use the entity tool? What do you use?
NT.
What command?
Oh, no tool commands. So the framework interacts with the Cassandra node probe interface. So in the node probe, there are a bunch of functions exposed, one of which is a replace function. So we just pass that this is the node I'm trying to replace, and this is the node I'm trying to add. So that function will take care of all that. Node tool, on the other hand, is a wrapper that works with the node probe interface, actually. So we are just essentially doing the same, but through a framework. Hmm. So if I understand the question correctly,
like the node doesn't need backup or those tasks you need. If you have an error, the DB or something supposed to log in using node 2 or one of those
So
What do you do?
one thing is we don't replace automatically yet because there are too many scenarios to consider before doing a replace. So if one node fails, we will wait to debug to see what really happened before hitting the replace endpoint.
Is the debugging process, what does it look like? Is it interactive or is it?
Yeah. So once the Cassandra cluster is launched, it's as good as the bare metal cluster. You just log in as if it is I'll show you later. It's as good as just a regular database.
So like a human interact?
Yeah, human can interact with it. Yeah.
So here you have this container management. Storage you can take from one node and attach to another node.
Mhm.
So we're replacing, did you guys do that? So
So-
take data from a dying node and put it on a new node.
So the only point we really do a replace is when the whole physical machine in which the data was died and it can never be recovered. Yeah, otherwise it's just launching the task again on the same node because the persistent volume is sticky and there is an ID which is associated with the task. So as long as the physical machine is alive, we can just launch the task again. Yeah. So yeah, all these are functions that can be called in a Cassandra binary. So the Cassandra provides a node probe interface for backup, repair. Everything's pretty much Cassandra supported here. We try to not modify Cassandra a lot because we want to. It's just a binary for us, and if we want to upgrade from 2 to 3 or 3.5, 4, we should be able to just replace the binary, and off you go. A little more information or detail into how a scheduler works. So a Mesos scheduler has three paradigms. One is a plan, the other one is a phase, and the other one is a block. A plan, for example, is launch 5 Cassandra tasks. That's a plan. And a phase is a what is this task about? Do you want to repair? Do you want to backup? What kind of task are you launching? That's kind of a phase because it still comes under managing the 5 Cassandra tasks, which is a plan here. So within the plan, we have phases. Just run the Cassandra task, or I want to repair it. Pretty much everything falls into a phase. A block is a block is a state at which a phase can be. It can be running. It can be normal. It can be killed. It can be lost. So a block is the state of a particular phase. It's available online, but I wanted to emphasize that this is something you need to consider if you want to design your own Mesos framework. So this is what is a Mesos framework. If you know this, you can just easily cook. It's kind of a cookie cutter approach. You can just develop something. You can take the Cassandra Mesos framework we developed, change a few things, and make it work with Mongo, for example. So, but the basic thing is plans, phases, and blocks. That's all it is. Any questions? So I wanted to do a live demo, but I don't know the internet here, so didn't take the risk. So I'll show you how I launch a Cassandra cluster in Mesos. So here, what it is this is a Mesos master. It comes with a UI, a bare bones UI, but it has a UI. So currently, if you see, there are no frameworks registered. Now there are 2 nodes registered with it. This is what we call the Mesos agent. So I have 2 nodes registered with this Mesos master, and each with 2 CPUs, 4 gigs of memory. Now I am going to launch a framework which will use these 2 agents to launch the tasks. So now what I'm going to do is let me launch a Cassandra framework. So here I'm saying framework, this is your Mesos server, this is your Zookeeper server, and this is the port you are going to talk to. And here I specify how many nodes the framework needs to manage, how many seed nodes, and what is the memory, the Cassandra CPU that I need, memory I need, and disk I need for each Cassandra task. That's it. So, yeah, so first thing it does is it registers with the Mesos master. The framework registers with the Mesos master. And these are all the APIs that come with the scheduler. So as you can see, repair/start. So this is one of the endpoints that if you want to launch repair, that's the endpoint that you'll be using. But as part of the startup, it is going to list all the endpoints. It's going to register with the Mesos master. Now it should show up as a registered framework. Yes, it did. And then as you can see, the node 0, or the first node of the Cassandra cluster, is being launched on the Mesos agent 2, which the agent that was registered with the Mesos master. The staging is nothing but getting all the binaries and setting up the executor. That's the staging part. Once the Cassandra binary is launched, the node goes to running again. Now it looks for resources to launch the second task. On the right pan, you can see the resources coming in, and the scheduler is evaluating each resource that it is getting from the Mesos master. And once the resource requirements are satisfied, it launches node 1. Then goes to the staging, launches the task. And that's it. We have a 2-node cluster up and running in a few minutes.
So how's your web app going to find this cluster?
Which one? That's the next slide. I'll show you. So I don't know. So this is the sandbox, really. So when I say a Mesos container, this is all the contents of a Mesos container. You cannot have a shared library of any sort. You have to bundle everything together. The container contains everything the binary needs to run. So that bundling part is very, very important. We even bundle the JRE with it so that we don't rely on the system JRE. For example, some of our servers have Java version 6, and Cassandra requires Java version 1.8. So we cannot rely on that. So we bundle pretty much everything together with each task that we launch. And it is typical of any cluster management system as far as I know. Yeah, again, just browsing through all the directories. And the Mesos here is pretty good. I mean, it's bare bones, but it lets you do all these things. So this is the seed provide I was talking about. Instead of providing a IP address, static IP address, we provide a URL to go fetch or know about the rest of the cluster. Yeah, so this is the URL it will be hitting to know. Yeah, so the plans faces part. Yeah. So now using the Cassandra cluster, to answer the question, now that we have 2 nodes up and running, it's essentially, you can just treat it as any bare metal cluster. You just have to give the IP address and it will connect to it. Because all it is doing is it's launching a task within a container, but the port is all shared. So when you connect to port 9042, which is the Cassandra port, you are still going to reach the Cassandra binary, which is running within the container. So any client, anyone, any service or any application can just use Cassandra like as it's running on a bare metal cluster. There is no difference to the services that we support. Does that answer your question as well? Oh, he had a question.
I want to know, is there any performance implication on
Oh, we have done that as well. I'll cover that later. Good question. You're always ahead, man. Yeah. So point here is once you launch the Cassandra cluster and it's up and running, it can be used as any other Cassandra cluster. There is no difference. Yeah, so as I covered earlier, Cassandra cluster just doesn't run by itself. We need to do maintenance operations. So this is where the framework is very useful for us. We use the repair endpoint. We use the cleanup endpoints to run periodic maintenance on all the clusters. Again, these are all automated. If you remember earlier, I talked about a Chronos system, which is a cron job in a distributed environment. So all we do is write a cron job, or a Chronos job, which will hit these endpoints for a particular cluster, and that's it. It will launch a task, and it's exactly the same thing. It will go from staging to running. It knows which node to repair or clean up, and it does its job, finishes itself, and you will never even notice what happened. So it is really convenient. Let's see that in action as well. So here, yeah, is our old cluster. We have 2 nodes running. What I'm going to do here, this is the important part. I'm going to hit the cleanup endpoint. So this is the framework URL, so the scheduler URL. And I'm hitting the cleanup endpoint. I'm just saying, for all the nodes, run the cleanup. Once I do that, you can see, I mean, it's really fast because there is nothing to clean up, so it already went to the finished state, but you get the idea. It was another task that was launched. It knows where to go, which node to talk to, which node to clean up, and then once it is done, it just says, I am done, goodbye, and then goes back. Similarly, repair or any other task or anything that you want to do custom on the cluster can also be a task. All you need to do is to implement the phase block, and the scheduler will take care of the rest. Any questions? I know it's a lot of loaded details, but any questions? Okay. So one other reason why we did the whole Mesos framework thing is the 4 nines availability, as I mentioned earlier. So this whole setup is pretty resilient if you think about it. So executor failure, if you go, which is the task failure, for example. If a task fails, the scheduler knows it and launches it immediately. Nobody needs to know anything. It will just launch immediately. And if it is crash looping again, we'll get an alert, which we need to look into. But in general, if a task fails just because of any reason, it will be restarted automatically. Node failure, as I mentioned earlier, it needs a manual intervention. We can automate that, but we haven't done that yet because the scenarios are a little complicated. Do we have to replace because the whole node failed, or it was not reachable? So that distinction is not very clear. Since our production systems rely on it, we still rely on manual intervention. And it's very rare that we hit a manual and very rare to replace a node. The good thing about this part is really important. So the scheduling framework, which was managing all the tasks, launching 5 nodes, launching repairs, launching cleanup, can and may fail. It's just a web app. It can fail. But the impact is very minimal. Your existing cluster will just keep running. Nothing will fail. All the Cassandra tasks will be running. The only disadvantage of a scheduler failing is you won't be able to launch any management task. You won't be able to add nodes. You won't be able to replace nodes. But it is not production impacting per se. You have some time to look at it. It's not red or code red. And the Mesos master failure, again, you don't need to deploy one Mesos master. You're going to have a bunch of services. So if one master fails, the other one would just take over. You would never even notice. And the framework will register with the new master. OK, so experiments. The whole thing was an experiment, to be honest. So we went with the Mesos version, which was not even GA. We developed this framework, and we did run into a lot of gotchas, but the whole thing is much better now. The Mesos is GA now. I think it's 1.12 or something. The agent is good. So the whole thing was an experiment which paid off really well, and we have been running it for more than a year. So one other experiment we did was the cluster startup time. How long does it take for a cluster to start up? For each node, this is the step that it takes. It receives an offer, accepts it, downloads all the Cassandra binaries, and launches the Cassandra task, right? One of the gotchas I really wanted to cover in this presentation is Aurora. We run alongside Aurora. So we have 2 frameworks, Aurora and the Cassandra Mesos framework. So one of the earliest gotchas we had was Aurora hogging offers. When somebody designed Aurora as a framework, they decided it is going to be the only framework that it will be running. It will never share resources with any other framework on that Mesos setup. So what Aurora does is it takes up all the offers. It will never let the offer go to a Cassandra framework. So that was, we did not expect that, but that was a good find initially. And then the Mesos will realize that it'll cancel or resign the offer, and then the offer goes to the Cassandra framework. So there was like a delay of 5 minutes. And then we were able to configure that to 10 seconds, which improved a lot of things. So here is the cluster startup time. To start a 40-node cluster, after changing the offer timeout to 10 seconds, it just took 40 minutes. It's like 1 minute per node. So it's pretty fast if you want to launch. And it is same for expanding cluster capacity. If you want to go from 40 to 100, maybe it'll take another 40 minutes, which is impressive. The other thing we did was, Aurora has its own quirks, so we decided to separate resources, dynamically partition the resources between the stateless applications and stateful Cassandra nodes. So that improved the node startup by about 30 seconds. So the other experiment that paid off really well is changing the garbage collector of Cassandra from CMS to G1. If you have not tried it, please do. It is worth it. It just really, it's really good.
What is your node setting?
Which one?
What is your
Cache.
cache setting? So CMS is good for after 8 GB.
So we use about 30 gigs.
So if you have
for
too much too big of a cache, then the problem is there will be a lot of pauses, right?
Yes, that's why we switched to G1.
G1 will also have
So G1 will split it into regions. There is no stop the world kind of a collection. Or there is like minimal stop the world collection. So we have seen like 1 or 2 max, but it's always like region-based collection. So that's why G1 really improved the performance for us. Otherwise, it's really difficult. So the latency, as you can see, the mean latency improved by a factor of 9 just with G1. So it is really worth it. I think with Cassandra 4, G1 is going to be the default garbage collector. It was planned for 3, but I don't know what happened. But yeah, G1 is worth it. It's, regardless of Cassandra or not, if you're using a Java application, I would recommend trying out G1 before, for all your benchmarks before launching into production. The other thing is, performance. Is there any performance penalty that we need to pay for running Cassandra within a container versus running it on a bare metal? So we try to find that out as well. So our setup is 3 nodes. This is our hardware setup. First, we ran Cassandra on the bare metal, measured read latency, write latency, and throughput. Then we converted those 3 nodes into a Mesos agents, launched the Cassandra tasks again, measured the latency again. As you can see, there is a minor hit which comes from, I think it's a C groups overhead that comes with each container, but it was negligible because of the advantages that our scheduler provides us. We just overlooked it. Does that answer your question as well? Yeah. Yeah, the throughput, again, it's pretty much the same. Write latency, again, really good. And yeah, so running across data centers, we need to, for this we had to make, a Mesos deployment is within a data center. It only manages resources within data center, but Cassandra can span across data centers. So we had to change the scheduler so that they can exchange seed information between data centers. So that is one change we made to the scheduler as well. And the last experiment we did was, how long does it take for the data to replicate from one data center to the other? You can imagine the data center being in East Coast and West Coast, so we measured that as well. So we write to one node, that's it, just one node. And then read just from one node on the other data center. And our P99 latency before the data showed up on the other data center is 47 milliseconds, which again is pretty good for most of our applications. So, and the round trip latency, as you can see, is 78 milliseconds. So very close.
What's your rights here?
One.
Right also one?
Yeah, right is one. Local one is in. So it's one replica.
Then you will get a spare data.
But this cluster is empty. There is no data on the other side. Yeah. So if it shows up, it's like the first copy that shows up. Yeah.
What about the throughput for replication? Did you have to tune window sizes or anything like that since it's replicating across such a long distance?
You mean the network?
Yeah.
No, we never did anything. I think our standard network worked fine. Yeah. One thing that I think we kind of changed the small message size. It's like buffer the small messages. We said don't buffer anything. Just as it comes, send it out. So that's one change we made.
How many nodes do you have in multi-disk environment?
Oh, our largest cluster is about 100 nodes here and 100 nodes here, like 200 nodes. Yeah. So overall, we have more than thousands of nodes in the Cassandra deployment now. So the Cassandra service is open source. We open sourced it last June, and we kind of made a lot of improvements to that. So if you want to try it, it's very easy. The tutorial, everything is available. You can just try it in your laptop, and patches and feedback welcome. So this is the team. Mesosphere guys really helped us in developing this because they are the Mesos guys, and Mesos was not GA at that time, so we required a lot of help, and they helped us, so we appreciate the help. And this is the team. I'm just here. The rest of the team is really here. And that'd be all. So I'd be happy to. Oh, yeah. Yes, so I think after we developed this, there have been a lot of efforts to bring Elasticsearch, MySQL, RongoDB, and a bunch of other stateful services to Mesos. If I remember correctly, there was a talk about running MySQL on Mesos last year during Mesos conference. So it must be already there, or it's already in the works, but it should be supported.
You have the containers connecting to the storage.
Yeah.
You put no dies, you just bring one and connects to the existing one.
Yeah, no. As long as the physical machine is alive, we'll launch the new task and attach the same volume to the new task.
How long does that server?
Few seconds. Yeah, so it does not that bad.
And is your Zookeeper cluster also, is Zookeeper also shared across the data center?
No, it's within the data center. The Mesos is within the data center. Zookeeper is within the data center. So all the state information about resources within the data center is managed by Mesos with the state in Zookeeper.
What kind of workload goes to Cassandra versus the schema?
Oh, schemaless. Okay. Good question. So schemaless is supposed to be if you don't know schemaless is a wrapper around MySQL. It's supposed to be a key value store. It's a key and a big JSON blob. So in terms of workload, what we use Cassandra for is it's mainly a geocache. If you look at it, it's we have a lot of mapping applications within Uber. We kind of have our own mapping infrastructure. So its main use cases are geocache and dispatch. So those are the main use cases. Schemaless, on the other hand, is for more persistent data. For example, I want to analyze all the trips. So once the trip is complete, it generates a bunch of data, right? That goes to schemaless. So yeah, that's what it is. So live systems here, and then rest of the data is schemaless.
How much you have to modify the Cassandra? Is it DataX or Apache Cassandra?
Apache Cassandra.
Just download and run it?
Just download and run it. The only change is the configuration change, which says get your seeds from this URL instead of here. That's all.
Is it that stable? You didn't have to make any changes?
We had to submit patches. Let's say that. We don't have any plans to maintain Cassandra in-house. That's kind of painful, and when a bug happens, we don't know where it comes. So what we do is we commit upstream. We have after we started this team, I had 2 patches, and then my teammates had 9, 10 patches. So they go out, get released, and then we take the release back to Uber. Yeah. So far, it's been working well, but I don't know. No, we just maintain our own. Cool. Thank you.